Hey everyone, welcome to the fifth episode of Robo Papers. We've got Georgios and Norman with us today, covering the paper R plus X, Retrieval and Execution from Everyday Human Videos. So welcome to the show, Norman and Georgios. Great to
Thanks
have
for
you.
having us.
Great to be here, guys. Thank you for having us.
Yeah. So maybe as a start, maybe Norman, you can go first, share a little bit about yourself. How do you get to do what you do right now? And of course, Giorgio, you can go next.
I'm currently a research scientist in robotics at Google DeepMind in London. I worked on the paper while I was doing my PhD at Imperial College in the same lab with George. And that's mostly it.
Cool. And George?
Georgios, it varies, I guess, from person to person, but I guess George is also easier to pronounce for
Georgios.
sure. So we did R plus X, I think back like mid last year with Norman at Imperial College, part of the robot learning lab. I'm still currently doing my PhD, so I'm finishing up now. And generally my research has varied from like doing sort of efficient imitation learning from just a few demonstrations, and then like basically the latest work that I've been doing is learning from human videos. So essentially, we're very interested in sort of finding different ways to use available data, because collecting, on robot data just takes so much time. And I think R plus X was essentially our first attempt towards that, to leverage sort of videos that you could collect in your everyday life. You just go about doing what you normally do. And if you have a camera, and I think as Norman usually puts it, like Facebook has this Meta Quest glasses and all that, and you could just go about your everyday recording what you do, and then you could just throw that into a robot, and then you could just learn how to do tasks on the spot, basically.
Very cool. Yeah, so I guess if you can share a screen, we can just...
This is our website. This is what the human videos look like. So we literally wear a camera. We go around the lab that we make it look like a house as much as possible, and we do these tasks and we record. So the videos are uninterrupted. There's no labels. We will talk more about this later. And this is what you do while you collect demo. So you just go on with your everyday life, and you wear this camera. When you want to use the robot, you just give a language command to the robot, and through a series of steps, it can execute what you ask for. I think one of the main ideas that it's in the title, so retrieval and execution, is that this work is based on in-context learning. So basically, we do not train any actual policy model. We just rely on entirely off-the-shelf models. In particular, we use an in-context learning method based on language models, so off-the-shelf language models. This is kind of orthogonal to the idea of using human videos, in the sense that the human videos part, it's one thing, and then we also show that with the in-context learning part, you can also just use, let's say, a large data set without having to train a network on it, by just retrieving what you need. So that at test time, you say to a robot, something, put this into the washing machine. You retrieve the part of the data that does that. You put it into this in-context learning method that we will see probably in a bit, and it works. So yeah, there's also this idea of not training anything.
Yeah, I think isn't it the holy grail? Like everyone really want to just take some videos and maybe especially just from human and let it work. So how's the setup? Like, how do you what when you say camera? Is it just like a GoPro? Does it have depth? Is it RGBD or RGB?
Yes.
So in figure 1 here, basically, so the human just wears that camera. In our case, we just have it strapped in front of our chest here, but you can just wear basically as a GoPro on your forehead if you like, or it could just be a camera that's like directly integrated on the glasses, right? And you just go about your daily tasks. In this case, we do use depth, and we can explain later a bit how we use it. But Norman, I think you were about to say something.
I don't know. I will go for it.
Okay. So basically, as you can see, like we just wear that camera. In this case, again, it's on the chest. You just go around, do whatever you normally do, and we just basically record an uninterrupted video of daily activities, right? That basically looks like, so thumbnails of the collected videos are shown on the right here. And then that's basically all you need as a
So you're saying,
human, right? So you need to do basically nothing else.
so you're saying an uninterrupted video of daily activity. So just to be clear, like that's like opening a door, opening a drawer, or like picking up a bottle or something like that. It's not like I'm just walking around my kitchen like cooking dinner.
Right.
How long or involved are these tasks that you're talking about?
It actually is the second. So
Okay, it's the
basically,
second one. All right.
is so what? So there's the theory in a certain sense, and then the practice at what we could do in a lab. So the idea is that you can have like a 2-hour video of you doing stuff. Realistically, we don't have enough stuff in our lab. So all these appliances that you see are toys that we were putting in our lab, including like the fridge was like the fridge of the. So in order to emulate what we were claiming is, so we recorded videos of several minutes in which we, for example, do some tasks in a room, then we walk into another room, we enter there and do some other task and stuff like that, and maybe that video can last several minutes, and then we stitch together several of these videos all together without any label to the model. So that can also, if we want, emulate what it will be like to wear these headsets on and off. But no, the idea is that it must be a single long video where you cannot have any external labels that say when you're doing what.
We have a small version of basically what Norman's discussing at the bottom of our website, if I'm not mistaken, Norman, if you want to go there. So if you scroll, I think at the bottom, where is it?
Oh, this one?
Below that. Yeah.
Oh,
so,
right.
So go for it, Norman. So that's sort of what it looks like. That's just one small part. Obviously, as Norman said, in practice, basically, it's me with a laptop in my back and recording everything. So we obviously don't have the storage to record like hours and hours of this, but this is how it sort of looked in practice, like an uncut, uninterrupted video, unlabeled.
Yeah, so I'm curious, Norman, you were saying something about 2 hours. Is that limitation because of the context window, the max context window you can throw in some kind of VRM? Is that it? Like, is there a limit to that?
So it depends in the sense that it helped a lot that we use Gemini. That, I mean, at the moment when we run the experiment was 1.5. So it was this model with like 1 million tokens that could fit an hour of video. So the first part where the language model is used, the VLM, is retrieving a part of a task. So for example, again, if you see a long video like this, I can ask the model, pick up the phone, and it has to retrieve all the snippets where a user picks up the phone. There's nothing stopping us from having parallel calls. So technically speaking, the context window is not even that important if you can have many more context calls. Obviously, it's better if it is a single call to a model. But yeah, this part in particular, the context window doesn't really matter because you can just, if you have like a 24-hour video, you can, and your context is like half an hour, you splice it up into like 48 videos, a bit more because you want to overlap a bit in case something is at the edge. And then you just call the model many more times. For the execution part that we will mention after, the real context length actually matters.
Got it.
But before we start going into the details of it, I think it would be great if we go into the website just to so like that we have a GIF overview of the method, just to sort of show, I think, all the steps, just to sort of give an idea of how like the structure of the whole R+X procedure works. So essentially, like, we collect the video shown basically on the left, right? As we said before, that's all you have, unlabeled actions. And then all you do is you just say, something like grab me something to drink. So you just prompt the robot directly. Then Gemini, in our case, comes into the picture. And as Norman said, you just retrieve the relevant clips, like give me something to call my friends. We get the semantic understanding from Gemini. We retrieve everything that has to do with essentially picking up like a phone, and then we extract specific features from it, in this case dyno features, and that goes straight into another model from a paper called key point action tokens, which basically work from Norman, that then gives you the actions, right? So just wanted to place in context where that retrieval part comes in that Norman just mentioned with respect to Gemini.
Thanks, George.
So So basically, so you're using key point action tokens as the kind of action representation here. Could you explain a little bit about what that's doing?
Yeah. Let me go back to the paper, which is a bit easier. So that's another paper that came out also last year that proposes a way to do in-context imitation learning by using off-the-shelf large language models and off-the-shelf large vision models to extract key points. The idea came by seeing that language models were good at more than just natural language, and then could also find numerical patterns and replicate these patterns. It has been studied for a bit. So I thought, can we actually put some demos into the prompts that we tokenize somehow into using the just normal characters, and can the model then repeat that? So what we need to find is a language of images and actions that you can put into a language model. So there's no images given to the language model in this iteration. What we do is we use large vision models to find semantic key points from different observations. Sorry, it's just this part here. So if you have several images of like a phone, you can use vision foundation models to find, let's say, 5 key points that are common, and that basically describe the scene as just a bunch of 3D coordinates that can be represented as numbers instead of all the pixels. So for each trajectory, so also each demo, your input are these few numbers in 3D that you literally write in the language model. And then the trajectory is basically the poses of 3 points on the end effector, 3 points to have a unique 60 pose that move over time. You just sample them at a certain frequency. So the actions are in the same Cartesian space, 3D points of the end effector. So you give to the language model these demos as pairs of the input key points are here, the trajectory was this. Now the key points are here, the trajectory was this. At test time, you just give the new key points of a new scene, and you say, can you generate a trajectory that follows the pattern that you have seen?
So this is why you need to retrieve those clips from the longer videos, because then you can pull out these keyframes, which I guess you're probably using Dino features. You're using, yeah, you said that already, right? So the keyframes are Dino features. So Dino features, if you're not familiar, are like these pre-trained features from Facebook, which are very like spatially, they're very stable spatially. They're so like you can track them over time. They tend to describe object semantics and other qualities reasonably well. So okay, so now so you pull out some set of these that as how they change over this, and that's also why you need the depth camera, because that then the depth for free gives you like this 60 trajectory of these keyframes of these key points. Are you doing any filtering to make sure that they're actually like all? What if I lose one partway through the clip? Like, what if I rotate my hand a lot or move too quickly and it blurs or something like that? Is that a concern?
I think so. We did a lot of engineering, obviously. I think there are some filters for that. Consider that another thing that we do, which is uncommon in papers, is, as you see, we actually have a moving camera, which makes things substantially more difficult. It's not scientifically interesting in the sense that it's just engineering, but it was actually a pretty big challenge that we also describe how we did that in the paper.
Yeah, I mean, it's robotics a lot of times. The test engineering parts are the hardest ones. So
because we wanted to emulate what it actually is to wear something and do some tasks, while several papers that learn from human demos have a 3D fixed camera, which will realistically never happen unless you always operate in a single part of your house.
Absolutely.
Yeah, so yeah, there are several filters, like if we lose track, there's also hand tracking. If we lose track of the hand at a certain point, we can just ignore the episode. So there are a few steps there.
Gotcha.
But so the main part of retrieval, as you were saying, is we kind of flip the question by saying, if we have an in-context imitation learning method, how can we rephrase this learning from large data? So now we show that there's an alternative where you don't have to just train a large monolithic policy on all the data you have collected and then hope it generalizes at test time. Another possibility is to have this large data set and just retrieve at test time what you need to then do, in a certain sense, retrieval augmented execution. That was another possibility for the title. obviously, I'm not saying it's the correct solution to solve robotics. There are pros and cons, but we show that there are several pros of, for example, using these large vision language models like Gemini that we will see later. For example, that you can ask a model, call my mom, and it will retrieve the snippets where you pick up a phone, which is something that it's very difficult to obtain from a language condition policy trained from scratch, unless you have a lot of data. So this was a way to show that we can transfer all the knowledge and reasoning capacity of these models into robotics without having to retrain stuff.
Yeah, I'm curious. In that case, let's say call your mom, right? And what if in your, let's say, long input unlabeled video, there's literally no clips that involve you picking up a phone, that kind of thing? Like, does Gemini say, sorry, I can't find anything? Like, is it aware enough to tell you that it can't find anything? Okay.
That's a good point. Yes, we actually tested that. So we tried to stress test it a bit to like, I think I said something like, make me a sandwich, and there's nothing close in the data set. And actually the model was pretty good already at saying there are no clips of that. Was because, again, it was 1.5 and today 2.5 was announced. But yeah, so it was pretty robust to that. And there are also additional filters where if you don't have enough clips of a certain action, you can ignore that. But yeah.
So a lot of this comes down to like the engineering angle of like, so, or like maybe it's the prompt engineering angle at this point of like which things are going to work well. Yeah. Fair. So what kinds of tasks I mean, obviously we can see some here, but how many things did you end up testing it on?
I think it was
Georgios,
totally 12, wasn't it, Norman? I think it was 12, right? Like, I think there should be in our experiment section. So we try to we sort of try to push this to do a variety of tasks in terms of like what's the manipulation skill needed, from things that, are probably simple, such as picking up like a can, to something that might be a bit more complex in terms of the trajectory required, like picking up, a deformable object like the pants there and putting it to do the laundry, basically, right? To things that just require, for example, pushing or like wiping, right? So essentially tasks that require different ways of like moving and interacting with objects. Also things like wiping or things like pushing, where you might not have like turn on the lights on the bottom right here in that figure. Tasks where you don't have like obvious, let's say, movement with respect to an object, I think were challenging and interesting tasks that we also wanted to tackle. And of course, when we sort of, in order to extract the relevant action, so one big question here always is, okay, so how do you go, from that human hand video to the actual robot action? And then, so in practice, what we did was that on top of, having Gemini actually retrieve the relevant videos, it was also fairly straightforward to get an insight on whether the task is actually just basically whether you're pushing and whether you're picking things up, right? Whether you're pressing, for example. And as a result, we sort of had different engineering procedures and different heuristics, which we basically used to extract, to map basically the gripper to the hand, right? So as you can see, basically in the figure here that Norman shows, we use basically a model called Hammers. It's basically a hand tracking model. It works impressively well. And then you can see the key points that we get on the hand mesh here in the third column. And then we basically use things like the tip of the thumb, the index, etc., to essentially fit the gripper into the hand. And depending on the task class, we have a different way to map that gripper to the hand to extract the action.
It would definitely be really cool if you could just ask Gemini to do this, like to tell you how open your 2-finger gripper should be instead of having to use Hammer, although I'm sure Hammer works better for now.
I just wanted to mention very quickly that we do this mapping because we didn't have a robot hand. Like if you actually have a humanoid with hands, you don't need to find interesting ways to like map a gripper to a hand, and you just map joints. You just mirror the position.
Well, that also depends. Like even with a robot hand, there's a lot of the 5-fingered hands don't have quite the flexibility and like range of a human one. So I think that in particular, there are some common ones which are just fixed off, which are like the episode.
Right.
We discussed this in one of the recent ones, actually. Yeah.
There's definitely a challenge, yes. Like still, if you had like, I guess, a 5-finger dexterous hand, you'd still need to do some engineering, but it would be
certainly
significantly
easier,
more straightforward.
Yeah. Yeah. Well, also you would think that maybe Gemini could handle some of this stuff. Okay. Sorry. But that's interesting. Just ask it like how, like, especially for the 2-finger gripper, it's like, I don't know if this is fully, like, if this is fully open and this is closed, like, what is rank it from 0 to 1 or something? I'm curious as to whether you could simplify the engineering work at all. No, but that's a tangent. That's, yeah, cool. All right.
So yeah, we're talking about the tasks, just
Yep.
to like give a flow to the paper, to the discussion. So yeah, as George said, we chose some tasks that represent some interesting family of movements, like reach, like wiping, pushing, a bit of precision, and then as I was saying, the main comparison that we wanted to do was against a large monolithic policy. So what are the advantages of decomposing imitation learning into retrieval and like immediately executing thanks to in context learning? And so the baselines that we used for the large policies were Octo, which back then was probably state of the art, if I remember correctly. And then another model based on R3M, which is a method to extract features from videos, and then a language diffusion policy head on top. This kind of, two large policies that you can think of. And the results were pretty good on our side. So we show that we are a bit better, even though this is not our main point, because obviously if you have a lot of data, the policies will catch up, while in context learning tends to saturate after a few demos. But I think some interesting experiments that we did were this family of experiments. So the first one we call hard spatial generalization. So what happens if at test time the object is in a very different position, an unusual position to what you have seen during training? For example, here we have a can placed on top of a microwave, which was unseen during training. And when it's on the table, all the methods are quite close, while when it becomes like a hard spatial generalization task, our method is quite stronger for two reasons. The first one is that it doesn't rely on full RGB input, but it has this key point bottleneck. So it has this information bottleneck where by using Dino, we just know where the object is more or less in 3D space. So we don't actually say the pose of the object, but we have some key points on the object. So we know where it is. And the second interesting part is actions generated by a language model. So the language model just generalizes to the fact that the gripper has to go close to the can wherever it is. So if the can is at a certain XYZ, it will generate a trajectory that goes close to that XYZ, whatever the numbers are. So if it is 000, or if it is 5,000, 5,000, 1,000 as XYZ coordinates, that's the cool thing of this kind of imitation learning through language models that I explored in key point action tokens. It can just understand the math behind the trajectory. And the second one is hard language generalization that we mentioned before. So what happens if I have an unusual way of asking for a task? For example, call my mom to pick up the phone, give me a non-alcoholic drink to pick up the can. We also have beers in the tasks. Or make the room less dark, which means turn on the light. The other policies basically completely fail on these tasks because the language command is too out of distribution. Even if we fine tune Octo, that it's already, if I remember correctly, trained on the OpenX cross embodiment.
OpenX embodiment. That's right. Yeah. So I had a question on that. How much did you fine tune Octo and R3M difflang, the language diffusion model on? So how much data are these things using compared to yours? Right.
So they start from the model as they are, and then we fine tune on exactly the same data.
Okay. So you're fine tuning on basically one or two examples.
The same data, but so to give the labels, we ask Gemini to label the videos, and so the videos are like pick up the phone, do this, do that. We actually try. So we have details in the end regarding how we did that. We also have success criteria for all of these things, if you're curious. The last thing is distractor generalization, which is very related to the spatial generalization, because also here, by using Dino to find visual key points, we can just ignore the distractors, because Dino will find matching features between all the demos and the test observation, and it will basically average out all the distractors and just focus on the can. And so this is pretty good for generalization when you have multiple objects, while if you just get RGB in, the policy has to be very good to generalize.
Yeah, makes sense.
Yeah, I have a question about how much we can stretch the scaling in terms of like the input of the videos. So let's say you put the entire YouTube, okay, somehow, and then you call in parallel context. Just call the hell out of this Gemini, and then presumably it can come up with even better, let's say, few shots examples. Would you say it's going to give you a bump to the success rate that you're already seeing, or your gut feel is that it's not just that?
So I think there's two parts, right? One is the retrieval part. So obviously, if we could just query all of YouTube and then just get more videos to feed into the basically key point action tokens, then probably we could get some boost in performance. Like I think on average here, we were conditioning on something like 10 to 20 videos per task, right? So, maybe if you go up to 30 or 40 videos, this could probably be helpful at deploy. So after you retrieve the videos, let's say the relevant videos to your prompt, when you feed them into key point action tokens, then it's likely that that would probably be useful. But I think as you sort of add more and more videos to it, probably as Norman mentioned earlier, performance will sort of start to plateau. And I think Norman has an interesting study on this also in key point action tokens, right? I think, Norman, where you basically compare what happens as you give more and more demonstrations to something like the diffusion policy versus basically doing in context learning, right?
Is this because you're fundamentally limited by the underlying like Dino features essentially here?
Not the Dino, the language model.
The language model.
Yep. We're doing in context learning with the language model with these trajectories. So I showed in the key point action tokens paper that after 20 demos, the performance kind of plateaus. So if you give 1,000, it's probably even worse at a certain point, because as you know, like language models, if you just fill the entire context, they might be a bit worse. Again, we're talking about Gemini 1.5. While diffusion policies can just absorb all the data you want, and so eventually they become better. But again, this is not about having the best state-of-the-art model. It's about a scientific investigation into a different approach to large monolithic policies, and in a certain sense, also like ways to fuse the things eventually.
I think
the big problem is depth. So for now, just to be very quick, so, we did some experiments, especially towards the end, to predicting depth. Roboticists know very well that monocular depth prediction is actually harder than it looks like, because a bit of flickering will make your model go crazy. It's very often not metric, and here it matters a lot. So if the mug is like 1 meter away or 1.2 meters away, it's a big difference.
Makes a huge difference. So
I
that didn't help out very much then, metric depth. So the real sense is better.
So real sense is definitely better.
Yeah.
We did try to get it to work with predicted depth. For something that doesn't require a lot of precision, you can get somewhere with the current models that we have, but it's definitely very challenging. Actually, I think just to continue from Mike's question on whether getting more data, let's say from YouTube, is actually helpful here, and comparing that with basically something like diffusion policies, I think Norman, we did also, like, if you want to scroll to that point, one experiment where we essentially compare what happens as you sort of bring in new tasks into your repertoire of skills, right? And I think the interesting take is While maybe if you have access to, 100, 200, thousands of demonstrations for a single task, maybe going straight and training, an end-to-end model might in the end actually lead to better performance. But if you want to add more tasks, so, let's say you have 10 demonstrations of picking up a cup, then you have 10 demonstrations of doing another task and then another task. So as you add more tasks into your into your demonstrations, as you can see here with R+X, you can immediately essentially use them, right? So you don't need to actually go ahead and train a network. So that's the number one benefit. And then the second one is also you don't usually get a drop in performance that you usually get if you sort of retrain a whole model on, a bigger data set that has a lot more variety of data, right? And the reason for this is basically because of retrieval. So for each task you want to execute, you basically only focus on what is relevant. So I think we can see like there's a great benefit there that, as you add more and more, like, you increase the variety of the tasks, you can sort of immediately leverage the demonstrations that you've provided, and also performance is basically just based on the demonstrations you have for that task.
It's basically, it's continual learning. So the idea that you just do continual learning without having to fine tune anything, which has a strong parallel with still language models, where in the a couple of years ago, when they just came out, they had the knowledge cut off, and so they had no idea what happened after. And obviously, you cannot just fine tune it every hour. Then, if you add the ability to search the web and retrieve the information, they are no longer bottlenecked by the knowledge cutoff. And that's basically the same idea, which we thought was very relevant to this use case where you just do tasks in your home, and maybe day one you have collected 2 hours of demos, and the robot cannot do much, but over time it just increases and improves, and you don't need to retrain it, fine tune it. It just recognizes new items in your house if you interact with them. So yeah, it's a simple way of tackling continual learning. Again,
So continual learning basically has this huge problem with catastrophic forgetting, which is what you're seeing here on the second of the blue and green plots, right? So basically the idea being that because you're doing this retrieval and you're not tuning anything, so it can retrieve the exact context it needs, and so there's no catastrophic forgetting. And yeah, cool, makes sense. Nice.
We also have a related plot here where we show what happens. So if you have more videos, as the performance of retrieval go down. Here we did a short videos, 4 minutes and 10 minutes, to see precision and recall of retrieval, and the performance is basically the same. We actually, again, worked with a total of probably 60 minutes of video. I think it was even a bit more. And we saw the performance was very good. It was very good back then. Now it's probably even better. So what I mean is there's no real risk of saying, okay, but if you have 10 hours of videos, it will probably start retrieving garbage. So the model is actually still pretty good.
This is like, yeah, that's one of the questions that I find really interesting about this kind of work in general is like, because you're mentioning it's probably even better now. Like, how much better do you think it is on Gemini 2, Gemini 2.5, etc.? Like, and why?
I mean, the jump of capabilities of these models has been quite drastic. I think Gemini in particular has very strong multimodal capabilities, so I think that's it's going to be particularly good. They also have in their official papers, the needle in haystack kind of task where you just put like a frame into a whole movie and try to retrieve that. Actually, so the original plan, now that I talk about this, the original plan for this figure was actually to put the videos into the Lord of the Rings movie. So something like that. So let's say I put some of the video we recorded into the movie. I think back then, probably copyrighted material was detected and you could not use it. So we just scrapped that. But we now have a very rare director cut of The Lord of the Rings, where every now and then there's just a hand grasping a mug out of the blue.
How to swing an axe and then you take up a
Exactly. Yeah, that's for the next mission. Thanks for the idea.
Yeah. Oh, that's amazing. I was wondering, like, does it matter if at all, like, those videos that you do retrieval from, like how close does it have to be in your, like during test time and the actual robot? Like you said, could it be in a Lord of the Ring kind of environment, and then you do it in a very brightly lit, like, you know, boring bedroom? Do you think those will also do very well?
Yeah, so I think that's a pretty good video here that actually Norman showed. So we like, obviously, you know, if it's in a very cluttered scene where you can barely see the object that you're interested in, so the demonstration that you retrieve, etc., it might actually be hard to, you know, extract something meaningful of, or if there's like a lot of, or if you basically cannot like properly see the hand. But we can actually sort of take videos that are in fairly what we would call wild settings, right? So you can see, for example, you know, picking up that Coke can there from grass, or basically opening up that box from a third point of view, right? So the camera is not, so we did videos where we don't actually necessarily need to wear the camera on the chest, and it still works. Now, you know, if you were super far away from the camera and you were barely visible, and the object that you're using was also barely visible, then maybe using that that demonstration would not necessarily be suitable. But I would say that it's fairly robust actually to the type of demonstrations that you use.
And I imagine the overhead of just adding this retrieval step, it's during test time, is literally just some kind of an API called the Gemini, and then you just wait a little bit and then do the thing, right? It doesn't, in practice, it doesn't actually, it's not like he has to think for a long time. Okay, let me check across all my archive of and find the right context. Right examples.
Yeah, so
Am I right?
the overhead, there is some overhead of the model that has to ingest the whole video and retrieve an answer. In our case, for half an hour of videos, 1 hour of videos, I think Gemini takes, it used to take probably less than a minute, but it's just, in a certain sense, it's random numbers, because if you just do 10 API calls with shorter videos, it will take less time, because now the videos are shorter and they're parallel calls. So it obviously comes down to what is your actual compute power. And for us, that's a bit of a vague idea, because we just give an API to one of the largest cluster in the world. So eventually it will be cool to run this locally. And I think that's also getting extremely closer to reality. Like the latest, I don't know, Gemma models are probably better than what this model was at the time. So the growth in small models, it's mind-blowing. So you can probably run something on like 1 GPU, 2 GPUs locally. So that, again, if you're thinking about an actual product, you can also promise, you know, privacy and stuff like that. But yeah, it's we run these experiments, as George was saying, a year ago, and in a year, this field, like the performance of this model has grown a lot.
Yeah,
And
so
even if it
literally what you're
takes,
saying
like-
is that,
Oh, go ahead.
sorry, Chris. Yep. So I suppose what you're saying is that you can take the same pipeline, you just need to wait as the field improve, right? You have better, like, you know, the, you know, vision foundational model, and then you have better like multi-model, you know, on the VLM side. You just need put in the latest model.
Yep.
This whole pipeline, you are expecting the success rate to just continue improving.
So this was probably the main topic of, I would say, a good chunk of my PhD, which was, so how much, the problem with robotics is data, as we know. So at first I explored ways to let the robot collect data on its own. And then I started exploring, okay, how much can we use these large foundational models that are, however, trained on completely different modalities, like text and just images from the web, like Dino. And so I have this plot in key point action tokens where I show the performance in imitation learning as you improve the underlying language model. In that case, I use the GPT models just because in that moment they were easier to put on a line chronologically. You know, you had 2, you had 3.5, at the time you had 4, 4 turbo, I think. And you see this line going up. So basically the same data, and the imitation learning performance just goes up because the underlying model gets better. And I think that's a very interesting point. Also, Dino it got better. So Dino V2 is better than one, but then they added this idea called registers to Dino that makes it even more robust and not finding like spurious key points. So I think this is a very important idea. It was also due to the fact that we do not had the computational power to train big models or things like that. So I was trying to see, okay, how can I actually use these existing models? And the results we got were pretty good. And I think it's quite cool that George and I showed that you can basically do learning from human videos with in-context imitation learning without running a single gradient descent step.
Yeah, it's really cool how approachable this is. Like how I think it seems like it would be pretty easy for people to pick up your work and deploy it, which is very exciting. And the other thing is, like, even if it takes a couple of minutes to process like hours of video, like that still presumably is a lot less than fine tuning on that video would take. So to go back
It
to
comes down to obviously how many times you will eventually call your model. So if every time you have to pick up a can, it takes 2 minutes, maybe you want to amortize that time by training overnight.
But why would I need to do it every time I pick up a can? Can't I just, like, if I know
Cache
that
it.
I'm going to pick up the can, can't I just process it once and save all those clips? Or is that
It's the usual memory compute trade-off in computer science.
okay?
So you're
Fair enough.
absolutely. It's even more engineering questions.
Yeah. How about? I mean, it seems like the tasks here are mostly pretty like you're kind of assuming that the task is the robot is already at that particular place, so there's no. It's just manipulation. Do you think you can extend this to mobile manipulation?
I'll also answer this, George, very quickly, just because I wanted to mention this other paper called, I think, Mobility VLM or Mobility VLA from Google, where basically they did a very similar approach, but entirely for robot navigation. So just wearing a camera like a phone and just walking through an office, showing all the different parts, and then you ask a model retrieve this from the kitchen, and you give the entire video to a VLM, and it will just find where the room is by just, again, like processing all the frames, and it will then probably like run a planning algorithm to go there. I don't remember entirely the paper, but yeah, that was also done, and these models can be very good for like semantic memory of a house, like understanding what is what, where did I see this object.
Yeah, so presumably, well, I guess here, yeah. So we keep bringing up YouTube, but obviously YouTube have no depth data. But you guys do mention that the depth in this case is pretty important. I think especially for the key action token part, right? I imagine.
I mean, depth prediction is
part-
another one of those things that's always improving. To be fair, so maybe
Yeah,
it
exactly.
gets better.
Exactly.
Yeah.
Yeah.
Sorry, go ahead.
I think definitely as the prediction becomes better, like you can sort of, as these models get better, you can easily like plug this into the current framework for R+X, and then just use videos, for example, that come from something like YouTube, like that basically don't have depth.
Yeah. So if I were to release like, it seems like this pipeline is wonderful. It's like magic. Like it's so easy to collect like human video data, and presumably maybe like a ton of them on YouTube, especially if the molecular depth estimation becomes so good, right? The models, each of them becomes better. Like where do you think is the limit? Do you think you can just have 100% success rate? Because right now, I think these are some of the tasks are still, like 50, 60, 70% kind of success rate, right? Where do you think where we'll somehow find a bottleneck and we need to then go and do that bottleneck?
George, you want to go for this?
Yeah, for sure. So, well, I think obviously the first question is, how do you go 100% from the human hand movement to the robot movement, right? So obviously there is an embodiment gap. And there's definitely like an open question on how do you actually cross that gap. So perhaps like, for example, if you want to do something that requires extremely high precision here, it might not be possible, mainly because of the gap between the embodiments, right? Especially if you're using a parallel GeoGripper like we do. And then I think that obviously based on the modality that you use and the quality, for example, of the key points that you extract, and if you have, for example, an object that's very deformable or part of it gets self-occluded during execution, so these are like scenarios where you might have basically challenges, let's say, during task execution. But for sure, like I would say that many, everyday tasks that we normally do that sort of require, picking things up, placing things up, or like setting up, your desk, for example, at your house, are things that as these models get better, something like R plus X should be able to.
And
I
it
agree
seems to
with that.
me,
Sorry,
yeah.
go for it. Go for it.
Yeah, and it seems to me just now you mentioned, I mean, at the beginning your setup is you wanted someone to put on the chest, but you also mentioned there are some clips where you actually the camera on the chest is recording someone else doing the task.
Yeah.
So presumably that constraint can also be removed so long there's some humans in the scene doing some stuff.
But that's an interesting point. So we recorded those videos actually for a rebuttal because a reviewer had exactly that point. They said, okay, but what if the camera, you're not wearing it? And we were like, that's actually the easy part. Having it in third person was by far the easiest part because, for example, we have all this part in the appendix where we show how we actually stabilize the video with key points. So you have to find, and this is another model. It's Tapir, where you have to find, now you have to do a very easy version of slam in a certain sense. So you basically just find a lot of key points, you see how the scene moves, and you try to locate the hand in an absolute 3D word frame that doesn't move. So yeah, that was a bit tangential, but that was to say that wearing a camera was a choice to make it hard and to give it a further justification that it will work.
Because
Just
verisimilitude, right? That seems more realistic for sure.
Yeah.
Yeah.
Regarding scaling this, what I want to say is the current in-context imitation learning key point action token is not magic, so it has clear limits since it's based on off-the-shelf models, and you also have experience in robotics beyond academia. Again, we didn't care about product in a paper; it's just scientific numbers. But the success rate that you have to reach for a customer to pay money for it, it's very, very high. Even if you buy vacuum cleaner, like a robot vacuum cleaner, even 10% of the times it was like, no, today I'm not cleaning. You'll be like, what do you mean? So it's
and this is like a self-driving car that crashes 0.1% of the time is a terrible self-driving car, right?
Yeah.
Like that's the go-to example.
I'm not saying that obviously papers should reach for that precision because again, most of the papers are just small labs trying to do scientific research, and it's interesting to see what other possibilities are there. Just saying that to answer your question, human videos are certainly a great opportunity, and we wanted to explore how to use them. But yeah, I think it's gonna take a bit before we can just deploy robots.
Yeah, I mean, well, one thing that is exciting about this, to me at least, is that even if this only gets you 60 or 70% on the way to the solution, that's enough that you could like start doing reinforcement learning or something from that point, right? You could like have the robot that solves the embodiment gap too, presumably, right?
I think
Yeah, exactly. I was just thinking like that even at test time, as you actually get the robot to do things, that those can be again, put back to to add in addition to your human video. So now you have the actual robot videos, and presumably those have basically no embodiment gap, and maybe you have this loop where it starts to learn from its own mistakes. You just put back to its own, like, retrieve its context, right?
Exactly.
Maybe human video is just a way to
I
get
think
things started.
that's a really good point. Yeah. So, like for sure you could sort of use all that, as a good prior for your model and then go and do reinforcement learning, right? Like all these trajectories that you get from the human videos are very helpful to kickstart, let's say, your policy, if you will, right? So it's definitely acts as a very good starting point to improve, let's say, learning efficiency. If you do reinforcement learning, as let's say Chris said, right? So if you want to deploy a pre-trained policy on these human videos and then sort of fine tune it with reinforcement learning to deploy the robot.
If you have a couple minutes, it would be good to. I would love to hear what your thoughts are as to the obvious limitations of the keyframe action representation that you used, because this is a podcast. I think there are probably people listening who don't know what those obvious limitations are, Norman. So
Absolutely. As I was saying, there are some clear limitations because it was mostly scientific investigation and it worked pretty well. But so the first part is the key points information bottleneck. So all information bottlenecks have advantages and disadvantages. So the advantage is it allows you, for example, as I was saying, to solve hard spatial generalization because you just know where the object is and you ignore all the other pixels. The problem is that you ignore all the other pixels and sometimes you cannot ignore them. For example, you cannot really avoid obstacles in this case, just as it is, or more nuanced information can become harder. A lot of tasks here are about, in the general robotics papers, a lot of tasks are about having to deal with a single object or with two objects. Some of them have to deal with entire rooms or like very large appliances like a fridge where just a few key points might not be enough. So that's the vision parts. The disadvantages of the key points. Regarding actions, the disadvantage is you're using an off-the-shelf language model in that case that is clearly not trained to do that. It's surprisingly good at doing that because they are actually good at geometrical thinking, mathematical thinking, but it's not trained to do that. So if you want to do in-context imitation learning and do like immediate deployment of a policy, it works. If you say, okay, I want to, as we were saying before, I have a single task, I have to reach 99.99% success rate, you might just invest on like a lot of data, reinforcement learning loops, and all this stuff to train a big policy.
Makes sense. And then there's also the embodiment mismatch and the, I guess, models like the grasp hammer and the viewpoint stabilization, all of which have their little pieces of error, I assume. But that makes a lot of sense. But I do think like there's still tons of value just in getting so close so quickly that you can actually start using these other things, right? Because like it starts the data flywheel turning, right?
Yeah, I guess maybe to wrap. Is there any other like things in the paper you guys want to highlight?
I think most of the other stuff are implementation details. We talked about the main plots. Probably the only figure we didn't comment is this one, which shows all the frames into a single long video, and then the green one are the ones that are
Selected by the
considered
retrieval.
for tasks. Yeah, selected for tasks, and we can see that the model can just ignore parts where you just like walk around or things like that. All right, here,
Yeah, so I guess a few like typical question we always end with. Imagine if you guys have like let's say 1 or 2 more months like more to wrap up this paper. Like what would be 1 or 2 additional things that you wish you have the time to squeeze into this paper that you think will make this an even more interesting one?
I think for my side, because we sort of tried for it, but there wasn't enough time. Like I think there was a lot more room to push for things where you learn directly from RGB. So I think if you use a model where you can get some predictive depth, even if it's not necessarily precise metric depth, you could still sort of scale it, to something that's close to real world depth just by getting basically, the average hand size, right? So you could still extract things like that would be useful trajectories to use. At the time, I think the best model that we managed to use was, I don't remember if it was Marigold or our Apple Depth Pro was out at the time, but
I think the Apple
both of
one
them
came
were.
out after because we
It came out
commented
after,
that
then
it would have
maybe I
been
was trying
useful
it
back
after
then.
then. Yeah, right. But I think that's definitely one thing that would have been good to add.
Yeah, getting rid of the depth, right? Yeah, it'd be
Yeah, I agree
interesting to
entirely.
see.
That's possibly the main part. The other parts we kind of tried everything. More tasks, but it's not super interesting. Then all the other limitations were mostly hardware limitations. So we had a Sawyer that's very well fixed into a room, so no way of moving that. With a parallel job reaper, so no hand. So if we had more time and more hardware, then yeah, like we did try to get another lab we tried to borrow a humanoid from another lab, but it was in the shop at the time, so no luck.
It's a constant problem with robots. Yeah.
Yeah.
Yeah. Okay, cool. But maybe one final question, I guess. Like, are there any other papers that you guys come across recently that like just completely blew your mind? That you just want to like give a shout out for too?
Well, for me, it has to be Gemini robotics, right? And I think Norman knows a lot more about it as he worked on it. For sure, I think it's like, one very, very impressive work, and definitely the results there, I think, are very promising on what you can do as you have more data and as you scale more when it comes to robotics. Both Gemini ER and robotics as well, I think. Very impressive work.
Yeah,
Norman,
that's,
how about yourself?
sorry, go for it.
And how about you? Like,
Yeah, no,
any-
okay. I have to say, I'm starting to appreciate probably a bit of a different kind of papers now, where, like, again, big models are fascinating, ways to generate data. Now I'm interested also in just tiny details regarding models. I think, yeah, the closest to this paper that we really liked was another one from, I don't remember if it was directly from Meta, but it certainly used the Meta area glasses. Was CMU probably. I don't remember, but it was a very interesting paper about doing similar things. And a very nice thing is that they use, again, these glasses, and then they put the glasses on the robot to have these.
I want to say that was Georgia Tech, actually. I think I know what
Oh,
you're
yeah,
talking
it's
about.
probably Georgia Tech. Yeah, I'm
I think
sorry.
it was
Sorry,
Danfe, right?
sorry,
Too.
people from Georgia Tech that are
I
listening.
go
Yep.
Mimic,
Oh,
right?
Yep.
Yeah.
One very cool thing about that paper, again, if you start thinking a bit more holistically about robotics, is that I think they still have an Aloha-like pair of arms, but they are mounted in a completely different way. So they're mounted as human arms. So basically, the base is attached in this
more like
direction.
shoulder.
When you start, even in our paper, when you start interacting more and more with the real world, the human world, you realize that everything is designed for our structure. So the fact that a lot of industrial arms are mounted like this starts becoming a problem, because the Sawyer arm is huge, and so it has a large workspace. But even when we try to open or close the microwave, you reach weird joint configurations. While for our body structure, you just do this, for example, and you open and close by just moving two joints. So that's something you also notice, and I start noticing it into different papers, like even just how the arms are mounted.
Yeah, makes sense. Yeah, that was something that you can't really tell with like a lot of these robot tabletop examples, like how the usable workspace where it can like actually move in a straight line is so small, for especially for the Franca like this is. So definitely interesting. Cool.
For sure.
Well, thank you guys. This was a really cool paper.
Thanks a lot for having us.
Yeah.
Thank you a lot for having us, guys.
Cool. All right. What do you think, Chris? Another great episode.
Yeah. It's really
what have you
interesting.
learned?
Yeah. Sorry. Go ahead.
Yeah. What have you learned?
Yeah. So what I like about this paper is that they talk about basically they have this nice system where you can wear a camera and you can actually just kind of like record a robot demonstration and actually just kind of replay it with like without putting a ton of effort into it, without like collecting a ton of data and doing a ton of fine tuning, and all these things are very finicky, right? So it's a very approachable way of getting robots to do all kinds of tasks, and they show a nice range, like including things like articulated objects like opening drawers and cabinets and things like, or they had a toaster oven or microwave. They've got like picking things up. So it works on a lot of stuff. It works on like real human data. So and it's all based on like Gemini, these robot foundation models. So yeah, cool work.
Yeah. I mean, I guess for me, the big thing is that like this pipeline that they have will just keep improving as they yank out. I mean, and replace it with the like latest foundational model, like the latest Gemini, the latest like Vision foundational model, the next version of Dino. So and they get all this performance just not changing anything. So and also human video is there's so much out there. So um yeah, I'd be curious where the bottleneck, like, because I mean, obviously this is a a scientific work done at an academic lab. So, but in reality, in production, I mean, if you really want robots at home, consumers are not going to be okay with 90% success rate. They're going to need 99%, if not more. Yeah.
Right. Well, I think a lot of that is like right now these models that it's trained on are not really trained on robot data, and this is like one thing that I asked about a few times was like whether or not was like how much Gemini, the newer versions of Gemini, are changing this, because like that's a really interesting thing that I think we'll find out from research papers over this year, because like Gemini is the first time that they've really started training these things on robot data. So what I would assume is that performance rapidly increases this year. Actually, that's what I would hope to see. And anyway, and I think it will. I think that's what we'll see. The other thing is that like so Dino is the same way. It's not really trained on this robotics problem. And if you had a way of like if Dino was like pre-trained for this, for key point tracking for robotics, I think you'd see massive improvement. So basically, and that doesn't change their method at all. This all changes without like, basically, if people start training on robotics data, which they will do as soon as that exists, so it's going to happen probably this year, right? Then we'll see all this stuff working even better, just magically without them doing anything, right? Which is kind of nice.
Yeah, ultimately, because it would just be maybe some API calls to some giant multi-model models that includes, robot action, as a modality, and then we just get it out of the box.
Right.
Yeah. But okay, cool. Well, yeah. Let's see the next one. Cool. I'll see you in the next one, dude. Okay.
Yep. See you.
All right.